Swayam Prabha. Digital India. Educated India.
In the previous lecture, we introduced dynamic balancing of rotors. Now, we will be extending those procedures in more detail, especially for rigid rotor case. We discussed in the last time that we can able to balance the rigid rotor using two planes, and one practical procedure of balancing rigid rotor in a balancing machine, cradle balancing machine I described. In that we saw that the method was hit and try. We need to place the trial mass at several locations and of different size, and then finally we need to converge what should be the balancing required in a particular plane. Now today we will be describing a procedure in which we require less number of measurement in the same machine, and then we will go for some other advanced technique of dynamic balancing of rigid rotor, like influence coefficient method, in which we not only measure the amplitude of vibration, but also we measure the phase information, which is very important information in rotor dynamics. So, with the help of that, we will see that how a rotor can be balanced on in field. So, that particular method is a field balancing method. We need not remove the rotor from the actual machine. Directly in the actual machine on the operating speeds, we can able to balance that particular kind of rotor. And then we will go for flexible rotor balancing procedure. We will outline a basic theory of modal balancing procedure. And so, basically the outline of the lecture is we will be briefing the rigid rotor balancing, especially we will be seeing the method, graphical method by which we can able to reduce the number of measurement required, which is very important in actual machines. Then will outline the modal balancing procedure, especially for flexible rotor balancing, and various terminology and concepts like influence coefficient for rigid rotor balancing, modal balancing, flexible rotor, dynamic balancing, modal eccentricity, orthogonality condition of the eigenvalues of rotor system. So, these are the things we will be covering in this particular lecture. So, now the same cradle balancing machine, but we will be using more systematic balancing procedure, and this procedure is after measurement through graphical method we can able to obtain what is the residual unbalance in one particular plane. So, in this basically we require only 4 observations of amplitude of vibration. So, first will be without any addition of the trial mass, we will rotate the rotor at particular constant speed and we will measure the amplitude of vibration. So, this we will be doing in the same cradle machine as we discussed in the previous lecture. Then in this particular case, because we want to obtain correction mass in one of the plane, let us say plane 2. So, we need to fulcrum the rotor in the at F1, and so in this particular case we will be obtaining the correction mass in plane 2. Then the same trial mass, now we can able to introduce a trial mass at convenient location onto the rotor. that convenient location we can call that as a angle theta, and this this particular angle we have chosen conveniently onto the shaft, and that will be the reference for the angle measurement. So, once we keep the trial mass, there will be change in the amplitude of the vibration when we rotate the rotor at the same speed as the first case, and that particular speed will be measuring it. So, this will be the second measurement. Then the third measurement will be the same trial mass will keep at 180 degree as so just opposite to this location we will be keeping it onto the rotor, and we will be measuring the amplitude of vibration. So, as we have done in the previous lecture, fulcruming at F1 and putting the correction mass in plane 2. So, these measurement these trial masses we are keeping in plane 2 of the previous lecture cradle machine, and the fourth measurement will be the same trial mass. We need to keep at 90 degree, either plus 90 or minus 90, and then again we will rotate the rotor at the constant operating speed, and we will be measuring the amplitude of vibration. So, basically we will be getting 4 amplitude of vibration. Based on these 4 measurement, we will be obtaining what should be the correction mass required at plane 2 when we have fulcrum the machine at F1. So, now let us see what are the measurement we have done, how to analyze. So, let OA is a vector, and the amplitude of this we know, and that is the amplitude of vibration when we are running the machine without any trial mass. That is the first measurement. So, this is basically first measurement. OB is the second measurement, in which we are keeping a trial mass at 0 degree. The trial mass is, we know the amplitude and amplitude of this. So, we have kept that at 0 degree, and because of this whatever the measurement is coming, amplitude of vibration, let us say that is OB. Now, because OB and AB, these are displacement, basically they are a vector quantity. So, we expect that the difference of these two vectors, because origin of these two are at O, and from there we have OA and OB, two vectors are originating. So, the difference of these two vectors, that means AB, will represent the effect of trial mass. So, if we have origin here and OA is this and OB is this, so AB will be the basically a vector which will represent, because this change is due to the when we are putting the trial mass into the rotor at 0 degree. So, this is the effect of trial mass AB. Similarly, the third measurement, that is this one, when we are keeping the same trial mass at 180 degree, let us say that is OC. So, is the vibration measured in trial run 3 with the same trial mass kept at 180 degree. So, now we can able to see that the same trial mass we kept at 180 degree. So, we have another vector OC, which is again starting from the O. So, basically AC vector, AC, which is A is without trial mass and OC is with trial mass. So, AC will be basically the same effect of trial mass, but when we kept the trial mass opposite to the previous one for the case of this. So, that means AB and AC vector, which are both effect of the trial mass, but in one case it has been kept at 0 degree for AB, and for AC it has been kept at 180 degree. The effect should be equal but opposite. So basically AB should be equal to AC, but they should have 180 degree phase difference because they are the effect of trial mass when we are keeping the trial mass at 180 degree phase. So basically AB should be equal to AC, but minus of this. So because they are having 180 degree phase. Now we have the following informations from the previous measurements and from the above analysis, that we have OA, OB, AC, OC 3 amplitudes are available, and we know that AB is equal to AC, but they have 180 degree phase difference. So these informations will be using it to construct a diagram, and from where we will try to obtain the what should be the correction mass and its location. So basically this is the diagram, but I will try to construct this diagram afresh so that the procedure is more clear. So first I am drawing a line OD, which is basically OD is twice of OA, because OA is the first measurement, and any direction we can take. So I have taken this as vertical, but any inclination we can able to take of this. So once we have drawn this, then we have two measurements, OB and OC. So we'll take these two arc, OB and OC, and skipping center here, we'll cut two arcs. So let us say this is OB, and another arc keeping at the same OA center, let us say this is OC. We don't know the position of the B and C, but we know they will lie on this arc somewhere. Now with the same arc, that means let us say OB, and we'll keep the center as a D, we'll cut this line here, and we'll keep at D and radius as OC. So basically this is OB, and this is OC. So we got these points, they will represent B and C. Basically we have obtained a parallelogram like this. So we got a parallelogram O, C, D and B. So basically this side should be equal to this one, and this side will be equal to this one. Now once we obtain this, if we want to join B and C, because this is lying in the two opposite end of the parallelogram, if we draw it, it will pass through point A, because A is the center of this parallelogram. So if we join this diagonal, this will pass through A. Now if we see what condition we obtained earlier, that AB was equal to AC, but they were 90 degree 180 degree phase difference was there. So AB is from here to here, this is the vector, and AC is from here to here. So and we know from parallelogram property, we know that these two sides will be equal. That means AB is equal to AC, and vectorially they are 180 degree phase difference because they are in the opposite directions. So that means we could able to construct a polynomial with the given property, the measurements. That means we have utilized OA, OB and OC informations and this property to construct this. So till now, if we go back to the measurement, we could able to utilize the first three measurement. The fourth measurement we have not utilized, that will be utilizing it. So before that, let us see again the construction what we have got. So in this what we will do now, we will take A as center and either C, AC or BC, because they are same as the radius, we will draw a circle. So let us say we are drawing a circle with AB and AC. Okay, so obviously it will pass, because the radius is AB, so it will pass through B, also through C. So this is a circle. This circle need not pass through D or O. From this figure you can able to see it is not passing through the D and O, but it should pass through B and C. Now our construction is over. Basically, now if we want to analyze this diagram, if we see, AB is the effect of the trial mass when we kept at the 0 reference. So that means AB direction is the reference, that is theta is equal to 0 reference. AB direction is that is 0 reference, and AC is when we kept the mass at 180 degree. So that means this direction is theta is equal to 180 degree, because when this is 0, so this has to be 180 degree, and 90 will come either this side if we want to measure the angle counterclockwise direction, or it may come this side if you want to measure the direction from in the clockwise. But how to decide whether we should measure we should measure the angle from counterclockwise or clockwise direction? So basically the fourth measurement, this measurement will give us the location of the direction of the angle, either we should use clockwise or counterclockwise. So let us say because of this we are getting a measurement which is OE. So OE is a vibration amplitude. So we will take OE as an arc, and if we are cutting the circle, so we will take center as O and we will cut the circle. If we are cutting circle approximately at the middle, if we are cutting the circle approximately at the middle, then let us say this point is E. Now we can able to see that this direction is 90 degree, because we have kept the trial mass at 90 degree and we are getting the intercept here. And if system is linear, we find that this particular angle will be approximately 90 degree. In this particular, here it is clear that E's intercept is perfectly at the 90 degree. So this particular point E will give us how we should measure. So we can able to see now the measurement of the 90 degree is such that we need to, so positive convention for the measurement of this will be counterclockwise, because this is the 0 line and this is the 90 degree line. So this should be the counterclockwise direction will be the positive convention for measurement of the angle. So and if the arc is cutting some other place, then the angle of direction will be changing. So let us say if our arc is cutting here like E prime, then what will happen? Then this AE prime is the 90 degree direction. That means we need to measure clockwise in this particular case. So measurement will be clockwise. So let us take that we got the intercept here, and based on this we have concluded that the measurement should be taken in the counterclockwise direction. Now our aim is to obtain the there is a residual unbalance and its orientation. So now we have seen that AB is the effect of the trial mass. So if AB is, because we know the trial mass, so let us say is having some number n grams. So if it is AB is equivalent to n grams, so what is AO? AO, we know that this is the measurement which we took without any trial mass. That means this is the effect of residual unbalance. So that means we can able to measure OA from this diagram, and we can able to find out what will be the equivalent unbalance in the form of, this will be O, in the form of grams. So AO length will give how much gram of unbalance we have, because we know AB is equal to some finite some number gram. So OA we can able to find from this relation. So once we obtain the value of the magnitude, the direction will be this one. So you can able to see this is the phase of the unbalance. So once we have decided this 90-degree counterclockwise, so the phase of the residual unbalance, which is AO, from the reference axis 0 axis 0 theta angle, this phi will be the phase of the unbalance. So in actual rotor, if this is 0 angle, this is 180, this is 90, this is 270, then we know that the unbalance is there at phi angle. That means this 0 phi. So unbalance will be here, and in this particular case we have kept all the trial masses at the same radius. So the radial position of the unbalance is known. We will be keeping at the same radial position, but magnitude will be given by this and angle will be given by this. So this is the same. So you can able to see this is the diagram which we have drawn, in which we obtain the position of the unbalance, and this is the actual disk. So in the actual disk, if this is 0 reference corresponding to this phi, which is residual unbalance orientation, will be given here, and for different cases given here. If intercept is at other location, how we can able to obtain is provided in this figures. Now this graphical method, in which we require only 4 measurement, will illustrate through one simple example. In this particular case, we are taking a single rotor, a single plane rotor, and we will see that how we can able to obtain the orientation and the magnitude of the residual unbalance using only 4 measurements. So in this particular case, we are considering a short flywheel, and we need to balance this, and we have 4 measurement, run 1, in which we are not adding any unbalance. The magnitude of the vibration is 6 micromillimeter. For run 2, 5 grams we are keeping at 0 degree. So this is the amplitude of vibration. Third run, this is the amplitude of vibration, and fourth run. So all run amplitude of vibration is given. Fourth run is at 90 degree. So we need to obtain the weight and location of the correction mass. So first run, let us say that is OA is equivalent to 6 micromillimeter amplitude of vibration. Run 2, OB is equal to this much, OC is this one, and OE is this much. Now with this we can able to construct the parallelogram, that is O, B, D, C, as we described earlier, and we can able to see once we have drawn the circle also, the intercept which is coming is here. So E is here corresponding to the 90 degree. So now we can able to see the measurement which we need to take, because this is zero reference line. So measurement is we need to take from the counterclockwise direction, because this is corresponding to the 90 degree, because the fourth measurement is corresponding to the 90 degree and the intercept is coming here. So we need to measure the angle clockwise rotation. So the actual position of the residual, which is residual unbalance, which is AO, will be given by this angle. So 360 minus 53. So that will be the position of the angular orientation. So basically this will be 360 minus this. And for amplitude, because we know what is OAB, which is equivalent to the given, there is a weight, weight is 5 gram, AB is the measurement. So AB we can able to measure it, that is 5.2, and that is equivalent to 5 grams, and OA is the residual unbalance. We can measure this also, and then we can able to obtain what should be the equivalent weight of the residual unbalance. So it comes around 5.76, and orientation is 360 minus 53 degree. So with this example, it's clear that how we can able to get not only the residual magnitude but its orientation also. If we are getting intercept here or here, that will decide how we should measure the angle, either from this side or this side. Now we will describe another method for rigid rotor balancing, that is called influence coefficient method. This is also called field balancing, because in this particular case we did not require any balancing machine. In actual machine itself, we can able to balance the rotor. Only thing in this particular case, we require measurement of amplitude of vibration as well as the phase information. And now let us see how we can able to. So basic method, the procedure first I am explaining. So basically there is a rotor which is mounted on bearings. In this case, generally rotors will be having access to add the mass or remove the mass at the ends only. So let us say L and R are two balancing planes. So here we can able to add or remove the mass, and near the bearing we are measuring the vibration by some sensor, maybe the proximity sensor or displacement sensor. So A and B are the measuring plane, L and R are the balancing plane. So first we will be rotating the rotor at some nominal speed, at some speed, and we will measure the vibration. So we will not add any trial mass into the rotor. Whatever the residual unbalance is there in the system, based on that we will measure the vibration at plane A and plane B, which are the measuring plane. Now because we are measuring not only the amplitude but also the phase measurement, I will explain subsequently how we can able to measure it. So let us we got a amplitude of vibration as y1a and the phase is phi 1a. So this is the measurement at plane A when we have not kept any trial mass. In plane B, similarly we got a measurement of amplitude y1b and the angle, the phase is phi 1b. So these are the two vectors which we have got it. That is due to the residual unbalance of the system of the rotor. Now in the next time, what we are keeping? We are keeping a trial mass in one of the plane, let us say balancing plane R. This trial mass will be knowing in magnitude as well as in the phase. What should be the orientation, that also will be knowing, angular location, and that angular location will be, so in the rotor basically angular location will be measuring at some fixed reference, always will be measuring with respect to some fixed reference. So once we kept the trial mass in the right plane, so obviously we expect there will be change in the magnitude of the vibration in plane A and B, even the phase will change, and we are rotating the rotor at the same speed. We are not changing the speed as we rotated in the first case. At the same speed we will be rotating it, so that we have the similar dynamic effect of the residual unbalance, and apart from that, whatever the extra mass we have kept in the form of trial mass Tr. So let us say because of this trial mass, now we got a amplitude of y2a, this is the vibration, and the phase of that vibration is, let us say, phi 2a. So both amplitude and phase we measured, and these are the, so this particular vector is representing the second measurement at plane A. Similarly, this amplitude, the y2b, is the amplitude of vibration, and the phase is phi 2b. So this particular vector is representing the vibration here for this particular trial mass. So now you can able to see if we put this vector here, and so from here to here, this vector, which is the difference of these two vectors, will be nothing but the effect of the trial mass, which we kept it in right plane, but the effect we are measuring in the plane A. So here we need to be we need to take care in which plane we are keeping the unbalance and at which plane we are measuring. So here the trial mass is kept in right plane, but measurement is in the A plane. So this is the effect of that particular trial mass on plane A. Similarly, if we keep this this vector here, so from here to here, this will be the difference of the two vectors which we have obtained without trial mass and with trial mass, and this will be the effect of trial mass which we kept it in right plane when we are measuring in the B plane. Similarly, now in the third case, we'll remove this particular trial mass from the right plane, and now we'll keep another trial mass in the left plane, and again we'll take the measurement. So let us say for this case measurement is this vector, this is y3a, and phase is this one, phi 3a. Similarly, in this particular case, y3b is the measurement amplitude, and phase is phi 3b. And again, if we keep this first vector here, this vector here, so difference of these two vectors basically will give, so this will give effect of trial mass in left plane onto the measurement in plane A. Similarly, this will be this difference of vector is the effect of trial mass which we are keeping in the left plane onto the vibration at the B plane. So basically with this, now we can able to get the influence coefficients. So you can able to see how we define the influence coefficient in the previous lectures, especially in the transverse vibration case. So this is the influence coefficient A or B. So A is representing the displacement where we are measuring. The second is representing the force where we are applying. So in the influence coefficient, the first subscript represent the displacement and the second represent the force. So in this, the force is applied at right plane because we have kept the trial mass there, and we are measuring at plane A. So this is defined as displacement. So you can able to see, because this is the difference of these two is the effect of trial mass. So this is the displacement due to trial mass Tr. So the ratio will give us this influence coefficient. Similarly, if we come here, this difference, which is y3a minus y1a divided by TL, will give a influence coefficient on plane A when the force is applied in the left left plane. On the same line, we can able to get two additional trial masses or the influence coefficients. So let us see those influence coefficient. So these are the first two, and in the right hand side we'll get two additional trial masses, that is BR. So this is the difference of two vectors in plane B, and this is the difference of vector in plane B for the third case, in which the trial mass in the left plane. So we will get four influence coefficients. So, and these influence coefficients now we are obtaining through measurements by measuring the displacement and its phase and the trial masses we know. So this is the first step in the influence coefficient, that we need to estimate the influence coefficient through vibration measurement itself. So once we got this, now we can able to obtain the correction mass in two planes. So let us assume that the correction balance masses in right plane is this one. This contain both amplitude and the phase information, because we need to know at what orientation we need to keep this unbalance, and this is in the left plane. So these two are known to us. So let us say these are the two variables which we want to find out. If we are coming here, if we are multiplying this particular force with alpha BR and this unbalance with alpha BR, so basically this quantity, because if you are keeping this particular correction mass in right plane and this in the left plane, with these influence coefficients we will get a displacement in plane B, because you can see in the influence coefficient the first subscript is B. So basically we will get the effect of these two in plane B in the form of displacement. So this quantity in the right hand side is basically is what is the effect of keeping this trial mass onto the plane B, because these are correction masses. So they should give equal and opposite displacement as we obtain in the case of residual unbalance. That means they should give us same displacement as this. This is in the plane B. So they should give this particular amplitude, but it should give the opposite displacement, so that this vector can get nullified, because these are the correction masses. So that means if we are keeping the correction masses, we expect that there will be no vibration at all. So that's why we have equated this equal to y1b, which is response due to residual unbalance in plane B, but minus, so that these correction mass are giving exactly same response as the previous one, but negative of that. Similarly in the plane A, so in plane A we have, so if we multiply these two correction mass unbalance with the influence coefficient alpha AR and alpha AL, we will see that this should give a vibration equal and opposite to y1A, which was corresponding to residual unbalance. So just equal and opposite, so that they should nullify each other and we should have net displacements as 0. So now we have two equations, and in this we have two unknowns, basically WR and WL. So these two equations we can able to write in a matrix form like this. We can able to rearrange them, and now we can able to invert this matrix. So if we have 2 by 2 matrix like this is the inversion of that in the closed form, where so lambda is nothing but the determinant of that matrix. So with that, if we invert the previous matrix, this matrix, we can able to get the WR and WL like this, where if we take the inverse of this using this formula, basically WR and WL will be given by these two quantities. You can able to see these are vector quantity. Generally we will be working in the complex form, so that we have the phase information and the amplitude information. So like if one of the vector, if it is ya, so this will be y1a EJ51A. So if we expand, we will get the complex quantity in the form of 1A real part plus J imaginary part. So once we have in this form, we can able to calculate what will be the orientation. So once we have got the WR and WL in the complex form, again we can able to calculate what will be the magnitude and the phase of the that particular quantity. This is the basically experimental setup of a test rig, rotor test rig. So you can able to see this is a two disc rotor system, and in this various instrumentation like amplifier, filter, oscilloscope and virtual instruments for data processing will be required. In fact, with oscilloscope itself we can able to balance it, but if we want to automate, we can use the virtual instrumentation for this purpose. The line diagram of the various instrumentations is like that. So this is a rotor. In this is the bearings. So left plane and right plane of the rotor is there. From at this location we can able to keep the correction masses or trial masses. There is this reference signal here. This could be a photoelectric probe. We can paste a tape onto the shaft that will give us some kind of reference signal, and all the phase measurement will be doing with respect to this one. In the subsequent slide I will be showing how we can able to measure the phase. Here on the bearing, or either we can use proximity probe or accelerometer to take out the measurements at these two locations. So in this particular case, these signals, first we need to send it to charge amplifier to or conditioning amplifier to condition the signal. There from there we can either we can send it to vibration meter to get the amplitude, or even this band pass filter we can able to use if we want to use. If there is a noise, we can able to use the filter. So before this vibration meter, we can able to put the band pass filter, and we can tune this to the rotational speed of the rotor, or through this photoelectric probe reference signal we can able to tune automatically this particular filter. And even we have phase meter which requires the vibration signal and the reference signal. So this will give the phase difference between the vibration measured at the bearing and with respect to this particular reference mark onto the shaft. Or alternately we can able to use oscilloscope, in which we can able to depict two signal. One is vibration signal from near bearings, and one the reference signal. So this I will be showing in the next slide how we can able to use oscilloscope to measure the phase if we don't have the phase meter. So basically this is the vibration amplitude with respect to time. So if we are filtering, we will get a nice sinusoidal curve corresponding to the unbalanced response, and this is a reference signal. So corresponding to the tape we are getting a spike. So we have kept the tape onto the rotor, because of that we are getting a spike. Now with respect to, we can take this as reference. So you can able to see from here one peak to one peak is the time period of the signal. For both the signal it will be same. Now if this is the zero reference, the spike, then you can able to see corresponding to this we have, so this is the reference. So next peak of the vibration signal is here. So you can able to see the time duration from this peak to the next peak of the signal is t1. So that phase difference we can able to write as 2 pi t by capital T. This is the phase leg of the vibration signal. So this, by that way you can able to measure the phase, because phase is a relative. So we can able to represent as a lag or lead. If we want lead, then maybe we need to take another time, but consistently we need to take a fixed procedure. So if we are taking from this spike to another spike, what is the time duration, that is the phase. in all signal we should follow the same procedure, then the measurement of the phase will be consistent. Now we will take up one example for influence coefficient method, and we will see how we can able to obtain the correction mass and correction mass in two planes, not only the magnitude but also the orientation of information of the unbalance. So, in this particular case we are considering a rigid rotor, and in this the machine is symmetric. That means the rotor is symmetric about its center line. So, a trial unbalance of 0.3 kg when we are keeping at end one of the end at angle 30 degree relative to some reference position. This causes change in the vibration vector of 50 microns at 61 degree. So, this is the phase we measured. This is at end 1 and 42 microns at 130 degree at end 2. So, what we have done, we have kept the unbalance, the trial mass in end 1 at certain location, and we measured the vibration in end 1 and end 2. So, plane 1 and plane 2 we measured the vibration corresponding to trial mass kept at 1. Now, we need to obtain the influence coefficient and as well as the correction masses in each of the plane, and these are the measurement without trial mass. Now, because this shaft is symmetric, so only we have one set of measurement regarding the trial mass, because these influence coefficients are also symmetric. So, symmetry we will be using in this particular case. So, measured responses due to residual imbalance are, so plane 1, these are the measurement. This is due to the residual imbalance without adding any trial mass. So, plane 1, this was the measurement which we can able to convert into the complex form like this. Similarly, in the plane 2, there is, we can able to convert this particular information in the complex form. As I described earlier, we can able to use amplitude of this and j theta angle. This will give us the complex quantity, because this is nothing but r1 cos theta plus j sin theta. So, once we have converted this to information in the complex form, now for trial mass when we kept in plane 1, this is the trial mass information. This we can able to convert again in the complex form. The displacement corresponding to this is in plane 1 is this much, and we can able to convert that in a complex form. Then displacement in the plane 2 this much, this we can able to convert in the complex form. Now, influence coefficients are defined. So, basically we are keeping the trial mass in right plane and in the right plane, and these are the measurement in plane B. So, this is the influence. So, we can able to put R2, R1, TR all there in the complex form. We can substitute and simplify. So, we will get the influence coefficient, this one. Similarly, alpha AR. So, trial mass we are kept in the right plane only, measurement in the other plane, there is the difference. So, you can able to see if you substitute this two which we have calculated earlier and TR in the complex form, after simplifying we will get this. And because rotor is symmetric, so we will be having like alpha 21 is equal to alpha 12 and alpha 22 is equal to alpha 11. So, this symmetry will hold. So, there is no need to calculate the other two influence coefficient again. So, once we obtain the influence coefficient, we know how the correction mass are related with the influence coefficient and the residual unbalance information. So, we can able to substitute in this expression and this expression to get the WR and WL, where this is determinant and this, if we substitute this influence coefficient, we'll get this information, this complex quantity. Basically this is within bracket. We can able to solve for WR and WL. So once we got this in complex form, again we can take the magnitude, that means the real part square, imaginary part square. If we take square root of that, will be the magnitude. So that means if we have real part square plus imaginary part and square root. So this will be the magnitude, and angle phase will be imaginary divided by real. So this will give us this angle. Similarly for the WL. So this is the correction mass in right plane, and this is the correction mass in the left plane. So now you can able to see we could able to obtain what will be the correction masses in two planes using the influence coefficient method. But in this we require the phase information, that is very important, and because of that we could able to reduce the number of measurement drastically as compared to the cradle balancing machine procedure. So in today's lecture we have seen first the graphical method for cradle balancing machine. In that we have seen that how we can able to reduce the number of measurement as compared to the hit and trial method, and in that systematically only we need to measure 8 total measurement to obtain the balance correction masses in both the plane of the rotor. And then we took up another method which is more advanced method for influence coefficient method. In that because of the now availability of the sophisticated instrument for measurement of the amplitude as well as the phase, we could able to exploit that information, and we could able to reduce the number of measurement to only 3 runs. Basically we need to run the rotor only for 3 times, and that is enough to find out what should be the correction masses in both the correction planes, not only their magnitude but also the orientation of that. In the subsequent class now we will take up methods for balancing the flexible rotor, which are more challenging, but because of the sophistication of the instruments which we have now, these procedures are quite developed, and now people have started practicing this in industry also. So we will see first very basic outline of these methods in the subsequent class, especially the modal analysis first we will cover, then we will go for the influence coefficient method for flexible rotor balancing.